Hello, everyone. Greetings, good morning, good afternoon, good evening, wherever you are. Yes, today we have a session and I'm presenting Matthew for a presentation that he's presenting in this session today. Matthew is a reader in Clean Energy with CCS in the School of Engineering at the University of Edinburgh. He holds a PhD from Imperial College London and worked in carbon capture technologies and clean low carbon energy with CCS since 2005. And in 2018, he started the first world massive open online course on CCS, which is freely available on the EDX platform. And to date, more than 13,000 people have worked and used that platform. Quite impressive. And in his research is mainly on developing CCS technologies that would be necessary to achieve a zero carbon society, which is the target of so many developed and developing countries that we are seeing around the world. And also the focus on his research includes integration of carbon capture for hydrogen production and also for thermal power plants, and capture readiness of power cycles, and the operational flexibility of CCS at the capture level and also across the CCS value chain, and also de-risking carbon capture in industrial environment. Also, Matthew is the principal investigator of the newest CCUS projects, which is funded by the ACT program, a three-year collaborative project, which is focusing on accelerating negative emissions in the waste to energy sector with CCS. With that, without further ado, Matthew, over to you for your presentation.
Okay, thank you, Fatima. So I'm going to attempt to slides. Yeah, so today I'm going to talk about cost reductions in CCUS clusters and what we can achieve by effectively integrating hydrogen and power production together. So effectively, it's a very long title to say that if you have a gas-fired power plant and a steam methane reformer that also uses natural gas, there are opportunities to reduce costs by sharing the CO2 capture plant. So before I start, I'm going to acknowledge the people that also contributed to this work. So Daniel Mullen at the University of Edinburgh, Dr. Laura Harris at the University of Edinburgh, and Professor John Gibbons at the University of Sheffield. And the initial concept developed here were initially funded by as part of the core research program of the UKCCS Research Centre. So this is what I'm going to talk about today. Why do we want to look at hydrogen and electricity in CCUS clusters? How to integrate a hydrogen plant and a gas turbine power plant? What is sequential combustion and how it can lead to cost reduction? We're going to look at case studies with commercial gas turbine and steam methane reformer designs. And then we're going to look at an advanced integration configuration that allows us to achieve higher efficiency and reach ultra high capture levels. And then we're going to look at what's the potential for cost reduction and then conclude with some thoughts as well. So why are we doing this? Hydrogen and electricity are two key low carbon vectors. They're likely to play a valuable role in decarbonizing the whole energy system. And as we develop our industrial clusters, it's very likely that in some location at least, they may be generated in the same place and benefit from a common infrastructure for natural gas supply, electricity supply, and the transport and storage network of CO2. This is to illustrate my point. So this is taken from a report from Element Energy for the Committee on Climate Change. So on the left-hand side, you have the 6 clusters that are currently in the government program, and on the right-hand side, you have a hydrogen infrastructure map looking at potential location for hydrogen production in the UK. And unsurprisingly, a lot of these locations are located in these CCUS clusters, and when they're not, they rely on some form of storage via ammonia. What are we looking at? So we're looking at a CCUS cluster, in our example, taking natural gas and some utilities, water, Okay, and then so from that clusters, in that cluster, produce power for decarbonized electricity, hydrogen, potentially other low carbon products that we're not going to discuss today. The CO2 can be sent together into dirigible storage, and there might be some residual emissions coming from that cluster, and we're going to look at also how we can reduce residual emissions as low as possible. So the question is, can hydrogen and electricity also share common infrastructure for CO2 capture? And if so, what cost reduction could be achieved? So first, I'm going to look at how to integrate a hydrogen plant and a gas turbine power plant. And I'm going to look at various options, various examples. So, but before I do that, I just want to talk through the conventional way of making hydrogen into a steam methane reforming. So, for those that are not familiar, so you take natural gas as feedstock, you heat it up, you start cracking the heavier molecules, and then that gas you put into a steam methane reformer where you put steam gas, you have a shift reactor, and you end up with raw hydrogen. And then that raw hydrogen you put into a hydrogen purification unit, and then you end up producing hydrogen. Out of your hydrogen purification unit, you have an off gas that contains some hydrogen that hasn't been separated, some unreacted methane, carbon monoxide, carbon dioxide, some water, and that off gas you're going to combust with a lot of natural gas into air to provide the heat for the reaction in the reactor and the steam methane reformer. And if you want to achieve basically low level of residual carbon emissions, you're going to use carbon capture. So you can capture the CO2 into a capture plant. You're capturing the carbon in the off gas and in the natural gas. Okay, so remember that there's an off gas and you are using natural gas as a feedstock, but you're also using natural gas for combustion. Okay, so now I'm going to look at 3 different options to integrate hydrogen and gas power plant, and all of these options are capable of achieving net zero emissions via ultra high levels of CO2 capture. So the first example, I'm looking at how we can produce 1 gigawatt of electricity and 2.3 gigawatt thermal of hydrogen from a hydrogen-fired gas turbine. The capture level is very close to 100%, and effectively, so that hydrogen-fired turbine takes its hydrogen from an SMR. So the SMR is scaled to produce the fuel for the turbine and 2.3 gigawatt of hydrogen. And then we capture the CO2. Obviously, there's no capture from the hydrogen-fired turbine. And if you do that, you basically with a hydrogen turbine that's got an efficiency of 62.5%, which is what commercial CCGT is capable of achieving. And we make a conservative assumption: there's no derating of the gas turbine. We use a solvent for CO2 capture that uses the element of energy that we scale up for 99% capture based on recent studies that have looked at high capture level. And we need to supply a little bit of heat to the SMR effectively to provide the energy for CO2 capture. And that heat is supplied in the best possible way, which could be extraction of steam from the combined cycle of the hydrogen turbine. And if we do that, basically to get 1 gigawatt of electricity, 2.3 gigawatt of hydrogen, we need an input of 6.1 gigawatt thermal of natural gas. So everything is in the same unit. So we've converted the natural gas by its calorific value into 6.1 gigawatt thermal of natural gas. Another way of doing the same thing, producing 1 gigawatt of electricity and 2.3 gigawatts of hydrogen, is to have a combined cycle gas turbine burning natural gas with post-combustion capture, and an SMR making hydrogen, producing a little bit of power and with the same level of capture. And if we do that, if you like, the natural gas consumption that we need is about 5.6 gigawatts thermal natural gas. So it's basically we knew that already, but it's a lot more efficient to burn natural gas, capture the CO2 to make electricity, rather than convert natural gas into hydrogen and then burn the hydrogen into a turbine, which is, at best has the same efficiency as the turbine using natural gas. So that configuration, though, may possibly exist in certain circumstances. So when would you use a hydrogen gas turbine? So this is now looking at cost of electricity production for a hydrogen turbine, comparing to a CCGT and a CCGT with CCS. And basically, when you have a low load factor, so 15% load factor, you see that the levelized cost of electricity is basically lower than the CCS with CCGT. And this is due to the fact that although the fuel costs are higher, the capital costs are much lower, since you're not capturing CO2 from the turbine, and obviously you're capturing CO2 upstream in the hydrogen production, and therefore you have a higher fuel cost. Now, if you look at basically base load power plant, 90% load factor, the hydrogen plant, the fuel cost of the hydrogen plant dominates, and the cost is much higher than the CCS with CCGT. So there is a role for hydrogen-fired turbine as low capex decarbonized peaking plants, but for base load or mid-merit power plants, hydrogen fuel costs dominate. So in our study here, we're looking at power generation options that are either base load or mid-merit. So we're not looking at hydrogen gas turbines. So now I'm going to talk about sequential combustion. So what is sequential combustion, and how it can lead to cost reduction? So sequential combustion is effectively making use of the excess oxygen in the exhaust gas of a gas turbine to complete a further stage of combustion and provide heat to a second process or a power cycle. And in that case, you can share the post-combustion CO2 capture plant between the gas turbine and that second process. These are previous examples that where we've looked at this for different configurations. So we've looked at this for retrofitting existing coal plants, when you're effectively trying to maintain the output of the plant when adding CO2 capture. Or we also looked at the way of basically producing additional CO2 for enhanced oil recovery in North America, where natural gas prices are relatively low. But in this context, we're applying this to steam methane reforming. So we're looking at an integrated hydrogen and baseload mid-merit power plant for cost reduction. And this is what a simplified diagram of the process looks like. So if you follow the gray lines, so you have the natural gas that you are reforming to make hydrogen. So it passes through the steam methane reforming. You have the shift, the hydrogen perfection unit, and then the off gas is produced. And now, instead of burning the off gas and natural gas into air, you are burning the off gas and natural gas into the exhaust gas of a gas turbine. So that gas turbine uses air and natural gas to produce electricity. You end up with flue gas at around 600 Celsius, and you do the sequential combustion in that flue gas. The heat is provided to the reforming process, and at the back of the steam methane reforming, you have a flue gas that's still very hot. So then you can put a heat recovery steam generator, connect to a combined cycle to make electricity, and then have a capture plant that effectively capture the carbon from the natural gas feedstock, the natural gas from the gas turbine, the natural gas used for the sequential combustion, provide the heat to the steam methane reformer, and the carbon from the carbon from the gas. Okay, so just wanted to now explain how it can lead to cost reduction. So I've put some very basic combustion equations here. Okay, so this is the stoichiometric combustion of methane. So you burn methane into oxygen to make CO2 and water. And when you burn methane into air, you basically have inert nitrogen that passes through your combustion system. So that nitrogen ends up in the flue gas. And if you look at the combined cycle gas turbines, so if you look at the combustion of methane with excess air, so in a heavy duty gas turbine, the sort of gas turbine system that we're looking at installing in the UK with CCS, you have an excess air of typically 150 to 200% to ensure that you protect the blade of the gas turbine, and you end up with an oxygen concentration of 11 to 13% across that range. So the excess air leads to excess oxygen that comes at the outlet of the gas turbine. Okay, so now this is the combustion of methane and the off gas in the SMR. So you're burning methane with some level of excess air, and so I've simplified the equation here, but you're not just burning methane or you're burning natural gas, and you're also burning the off gas. So, but basically, you end up with a similar combustion and some nitrogen that effectively passes through your system. So again, this is the diagram of the SMR. So the off gas is coming here. You have the natural gas air that you are combusting into the furnace to provide the heat to the reaction. And effectively, what we propose here is to use the excess oxygen in gas turbine as the source of oxygen for the combustion reaction in the furnace of the SMR. So now there is no additional entry of oxygen or inert nitrogen into the SMR other than that from the gas turbine exhaust. And effectively that leads to a reduction of the amount of flue gas that you put through your capture plant. So here, this is a base case with an SMR and a CCGT in parallel. And here you can see the total volume of flue gas that is going through your system. And if you have an integrated case, effectively you have avoided nitrogen and oxygen that you're not using into the SMR because you're using the gas turbine flue gas, and effectively that reduced the total volume of flue gas by about a third into your process. And this is what we can use for cost reduction, having a smaller CO2 capture plant. Lowering the total flow rate, reduce the capex of the capture plant, and also we end up with an increased CO2 concentration at the in the flue gas, so we can reduce capex and opex in the CO2 capture plant. So we've done some case study with commercial gas turbine and steam methane reformer design. So I'm going to go through them briefly. So we've looked at an H-class gas turbine with a steam methane reformer. So, so an H-class gas turbine is the largest class of gas turbine. This is sort of plant that gives you with a combined cycle 800 megawatts of output. So we're looking at an existing one from GE, the largest available, and with that gas turbine to scale our system, we effectively need to have a capacity of the SMR that's about 3 times the size of the largest commercially available SMR. So that's not necessarily a problem because you can either build a very large SMR or you can install 3 SMRs in parallel to do the same thing. In any case, if we're going to ramp up hydrogen production with CCS, we're going to have to build more or bigger SMRs. It's nothing too extraordinary. So the GT supplies flue gas into the SMR. We burn natural gas, gas, make steam, make electricity, and capture the CO2. And this is showing you the detail of the furnace. So this is in this example for this type of SMR, it's a radiative furnace. So effectively, you will be burning your natural gas and tail gas into the burner, and your oxygen source will be the oxygen from the gas turbine. Okay, this is the integration, so showing how you can recover heat from the flue gas. So here you have the flue gas into the SMF furnace, supplying heat to, in purple is the effectively the hydrogen production process, and on the right hand side you have the integration of the heat recovery steam generator with the combined cycle. So what we find when we look at this configuration, we find that the larger flow rate in the SMR reduced the adiabatic flame capture from about 1800 to 1570, and effectively that changed the mechanism of heat transfer in the SMR. So you're moving from radiative heat transfer into more sort of convective-based heat transfer. So we've also looked at a second option with a convective reformer, and we're also able to provide additional steam generation in the system. Now this is showing the results. So if you have a base case with an SMR and a CCGT capturing 90% of CO2, and you compare them with an integrated system, so they both scale to have roughly the same hydrogen production. The natural gas feedstock is the same. Natural gas fuel for combustion is roughly the same, and we find that we have an additional power output of 67 megawatt. If you look at the capture plant, the flue gas flow rate is reduced, and instead of having 3 absorbers, 1 from the SMR and 2 for the CCGT, in that case you only have 2 absorbers to capture the CO2. So 30% reduction in the flue gas. Effectively, the absorber of the SMR in that case becomes redundant. You're now capturing CO2 at 15% concentration by volume compared to 4.5% in the GT, and the net power output increases by 11% with a fully subsidized absorber for the SMR. Now this is showing Port Arthur in Texas. So this is a 1 million ton of CO2 per year hydrogen production plant. So the CO2 is captured by the hydrogen is separated by a pressure string absorption, and the capacity of the plant is 1 million ton of CO2. But what I wanted to focus is looking at the flue gas pathways, and this is to show that this is done at relatively large scale already. So in this example, you have a natural gas fire turbine. The gas turbine exhaust comes here, is split into 2, and this is a second stage of combustion that is used to supply heat to the SMR. So effectively, this is a sort of a smaller configuration of the sort of configuration that we're looking at here, but it's commercially available and been operating for several years. Okay, and now we're looking at a different type of SMR. So smaller SMRs where the heat transfer is basically via convection. So the principles are the same. We now start with a smaller gas turbine, an aeroderivative gas turbine, and we find that this off-the-shelf gas turbine would have to, and we take the largest commercially available gas-heated reformer. We find that we'd have to increase the size of that gas reformer by 50% for the purpose of our configuration. So again, nothing too engineering challenging. This is showing how you supply the heat to the SMR and the reaction of the natural gas. So you basically burn natural gas, and then you have a convective heat transfer. Your process gas enters in those tubes here. So that's right. A zoom section here of one of the tubes is shown here. So in the red box. So the process gas comes here at 450 degrees, goes through the catalyst, and then leaves at 600 Celsius. And effectively, you have flue gas coming here at 1000 to 1200 Celsius and leaves at 800 Celsius. And that flue gas can come from air, or it can come from the combustion of natural gas and the off gas into exhaust gas turbine. Okay, so we've done the integration, and similarly, we find that if you compare a scale plant to have the same hydrogen production, you find that you have an additional power of 14 megawatt compared to the 71 megawatt that you'd be making. So the 57 that you'd be making. In terms of flue gas flow rate, you've got reduction of 30% of the flue gas flow rate, and instead of having 2 absorbers, 1 for the gas-heated reformer, 1 for the CCGT, you only have 1 absorber now for your CCUS plant. And again, so you have you could argue that you have one of the absorber that's redundant, and that you increase your net power output by a quarter with a fully subsidized absorber. So this is with off-the-shelf configuration. This is a summary of the results. But we can also look at better integration of the power cycle that's located after the SMR. So there's a third option that we've looked at more recently, and we've called it the advanced integration in this presentation. So we find that there are further improvement in efficiency by making best available use of the hydrate heat available for power generation, and we also have the same benefit in terms of CO2 absorber reduction. So effectively, this is a more complex diagram, but effectively, what we are doing here, we are improving the heat recovery. We are modifying the one of the turbines so that it operates at a high pressure turbine, and then we are improving the heat recovery of the within the reforming part of the process. Again, this is the diagram showing the integration of the steam production with the various hot gases and the syngas. There's a part in that heat recovery steam generator where you would have to operate above the 820 Celsius, which would require, we think, more expensive advanced alloys, but it's not something that's done in other processes. So compared to a conventional SMRH, there's a little bit of an increased cost here. So if you do that, what we found, so we're comparing a base case that has a CCGT and an SMR in parallel, a case with the direct integration with a off-the-shelf gas turbine and commercial SMR that are adequately sized, and an advanced configuration. So we're looking at 90% capture. The hydrogen output is the same in this example. There's a reduction of flue gas flow rate. This is the concentration of CO2, and I should have also put a green rectangle here showing the efficiency. But what we find is that compared to the base case, if you size for the same hydrogen output, so you allocate all the efficiency saving to power generation, you increase the power generation by 13 percentage points, or 6.5 percentage points compared to the direct integration case. In our examples, that's an H-class CCGT with sequential combustion radiative. So you can drastically increase the efficiency if you make basically a purpose-built heat recovery steam generator. Now, what we're looking at is we are looking at how you can use those efficiency improvements to achieve ultra high capture level. So as you increase your capture level, the energy penalty of your capture plant is going to increase. We find from recent studies from other vendors, MHI or R&D colleagues in Australia, that and also modeling studies, process modeling software, that effectively what you can increase the capture rate of a post-combustion capture system at a marginal increase of the energy penalty. I showed the numbers earlier, so we think that you can achieve those high capture levels by increasing the reboiler duty of your capture plant by less than 10%. So if you do that, effectively, so we're looking at now our direct integration case. So this is the CCGT SMR, the off-the-shelf configuration. We have an electrical efficiency of 64% at 90% capture. And now if we look at an advanced integration case with a purpose-built SRSG, and we're looking at capturing 99.8% of the CO2, basically that increase in efficiency more than compensate for the energy price that you pay for increasing the capture level. So in other words, you can achieve, if you like, very close to net zero hydrogen production and power production at an efficiency that's higher than either conventional case or a case that's integrated off-the-shelf system. And if I go back to my previous comparison, where I was looking at making 1 gigawatts of electricity and 2.3 gigawatts of hydrogen, we find that the natural gas capacity that you need is 5.1 gigawatt thermal. And effectively, that's a further 9% reduction in fuel compared to the 5.6 gigawatts with the base case, the non-integrated SMRH CCGT. So what's the potential for cost reduction? So now that we have one carbon capture plant that's capturing CO2 from the combustion in the gas turbine and in the SMR, how can we use that to reduce costs? So basically, the cost reductions come from the reduction in the size and the number of CO2 absorber, the flue gas conditioning, and all the absorber ancillaries. If you think about your CO2 capture process on the regeneration side of the process, nothing has changed because the volumes of CO2 haven't changed. Same with your CO2 compression system. So you're capturing all of the CO2 from the SMR and the CCGT. You have a reduction in the size of the absorber and their numbers, but your stripper and compression are still the same size because the volumes of CO2 haven't changed. Now, if you look at capital costs in public domain FEED studies, you still find that there's a large discrepancy in capital costs. So I've never been really comfortable with doing sort of cost studies because of the uncertainty that of any of these costs, but I've attempted to do that here. And what we found is that 2 FEED studies in the public domain show absorber capital costs. So we've used those data. So this is the FEED study that we've used. So Karlsruhe Gas Nova, it's a CCGT plant in Norway using 35% MEA. Costa Rica was a study done for the World Bank, CCGT retrofit using 30% MEA. We have the Road CCS project, so that was the 4 plants in the Netherlands in Shelf. Use the economic fuel process. Shand SAS Power in Saskatchewan, MHI, and a FEED study for an Australian coal plant with 40% MEA. And also some Petranova in Texas that use KS1. And what we've done effectively, we scaled our system using a methodology that's available online in the public domain by NETL, and they effectively use a fairly common method of so you scale your cost on the basis of reference cost. And you have a scale parameter and a reference parameter that you use with an exponential. So the guidelines, if you like, are that for the CO2 removal system, this is the exponent that you should use, and for CO2 compression drying, this is the exponent that you should use. And you should allocate 40% of the cost to the gas flow, and the remainder should apply to the CO2 capture plant. We're using their methodology so to report costs, and effectively what we found for these FEED study is that we scale for 300 kilograms per second, which is the size of our absorber for our integrated case. There's a huge discrepancy in cost. So if you scale now on so capex $1 million per kilogram of CO2 per second, you find that the average is around 5, but the standard deviation is pretty big. And in a way, it's not surprising. We're looking at existing plants and new plants, different solvent, but still it's still a large standard deviation. So having said that, and taking that caveat, you know, the numbers I'm going to present are basically comes with huge uncertainties as well. So what we've done for the UK, we've taken the report that was done for bees by Woodbrook, and effectively we've taken their cost for an SMR, a CCGT. So you have the this is the size of their plant, and we've scaled it to our purposes, and we basically find a capex, so $1 million per kilogram of CO2 per second, and also they use solvent from Shell. Effectively, if we do that, and if we use the fact, I should have said that in those two feed studies, Castor Gas Nova with MEA and Loyang Bechtel, the capex for the absorber is about 16%. So if you use that that value and we scale for our system, so we're now looking at 1 gigawatt of power, 2.3 gigawatt of hydrogen. We find that we can get a capital cost reduction if we include the CO2 compression frame close to 10%. So those costs are for capture plant only. We haven't included the capital cost for the SMR or for the CCGT in those numbers. And there are further cost reduction possible if you reduce number of plants. You might also do a further saving, and also if you reduce the number of steam cycle you have in operation, you might do some savings that are not accounted for here. To conclude, so we find that you can integrate hydrogen plants and CCGTs in CCUS clusters. There's no technical barrier identified for the concept of sequential combustion that we propose, although larger conventional designs would be needed. If you do effective thermodynamic integration, you can reduce fuel costs by 9%. Compared to having a CCGT and an SMR in parallel, and the reduction of the number of absorber leads to capital cost reduction of about 10% of the capture plant capex. Now, in terms of thinking how you can use those cost reduction further, so if you have if you think about a cluster, you may have a CCGT that's operating as a non-base load power plant, and your hydrogen production may also be non-base load. So if you're able to combine the absorber and the capture plant of the two processes, effectively you will result in a higher utilization factor of your CO2 absorber, and that would lead to reduction of the levelized cost of electricity with CCS and the levelized cost of hydrogen. But we haven't quantified that yet. And yeah, so that's my final slide. So further thoughts on this. So more detailed capital costs and techno-economic analysis are necessary. I think this is now the sort of work that academics can do, but if you want to understand the potential for cost reduction further, you want to do a sort of fairly detailed engineering study. There's a question about also how you can understand the flexible operation of a combined hydrogen and power plant. So can the gas turbine, the SMR, and the capture plant cope with the variability of output? So if you turn down your gas turbine but not the SMR, or if you turn down the SMR but not the gas turbine. So this is something that we want to look at further. In terms of business models, so because the cost reduction are not necessarily directly attributed to the gas turbine or the electricity production, or they're not necessarily attributed to the hydrogen production, is how do you capitalize on those cost reductions? So you can imagine that if you are a project developer and you're looking at producing hydrogen and power together next to each other, it might make sense, but at the moment I think that's unlikely. So what we're saying is electricity utilities building CCGTs, and we're saying sort of oil and gas company building SMR. So then you need to start thinking about how you could allocate this cost reduction if you have a separate hydrogen and power production plant. Potentially have a third party operating the capture plant. This third party could be either the hydrogen plant owner or the power plant owner, but basically I think it's saying yes, you can reduce cost, but how you allocate that in that example is not necessarily straightforward commercially. And I guess it sort of leads to a more generic question: is how do you allocate cost reduction in shared capture infrastructure and clusters? So, you know, as we build these clusters, the location of the transport and storage infrastructure is going to be, you know, dominate the you know, the decisions that you make in terms of where you locate your assets. So it's possible, and also I would say very likely, that we might see a lot more options for shared capture infrastructure. So how do you allocate cost reduction between potentially two different businesses? Is it too difficult? Would you bother? I think we don't have the answer yet. And also, who benefits? So is it the plant owner? Is it the taxpayer that's effectively subsidizing either CCS electricity or potentially hydrogen made from CCS? Or is it the end consumer? So how do you pass on those costs, and who do you pass them to? And again, I think if you want to, I think, take this concept forward, we've done the engineering analysis, but a lot of these questions need to be answered now. Okay, so I think that was me. Thank you for your attention, and yeah, hope we can have a few questions and a good discussion.
Thank you, Matthew. That was really interesting and well presented. And I see that, you know, huge effort has been put together to do all these cases. That is excellent. Yeah, we can have a round of questions. I also have a few questions that I can ask, and let's see if we have any questions from participants before me asking you the question. I think, Vincenzo, if you have a question, could you please unmute yourself and ask the question?
Yes. Hello, Mathieu. Thanks for the very, very interesting presentation. So my question is more general, I would say. So you really gave us a great overview on conventional and some advanced version of conventional technology, both for hydrogen and CO2 capture integrated, as well as for advanced gas turbine cycle. So my question is more, considering your cost reduction and performance improvement, how do you see the use of new technology? So let's say I mentioned here membrane gas solid reaction, but there are also definitely other for CO2 capture and hydrogen separation, and also from the power generation point of view, do you think those figures that you were presenting could be improved, highly improved, if you use fuel cell or other technology compared to the one that we have at the moment for power generation?
Yeah. Okay. So yeah, that's an interesting question. Yeah, thank you for that. I think in a way, a lot of the work that I've done so far in my career is I tend to look at post-combustion and CO2 capture as a generic technology, and I look at MEA, generic solvents, but a lot of the integration happens upstream of the post-combustion CO2 capture process. So as a generic principle, reducing the amount of gas that you're going to put through your CO2 capture process, increasing the CO2 concentration, is bound to lead to cost reduction. Now, if you choose to use a membrane system or you talk about gas solid reactions as well, absorption system, you would also look at cost reduction. We've limited our analysis to the amine solvent, but I think you would also see cost reduction for other types of post-combustion capture technologies. In terms of fuel cells, I don't know. I think yes. I think we haven't looked at that. I think there's potential there. So I presume you're thinking about the process where you combust natural gas in the flue gas to run the fuel cell. Essentially, yes. So I think the integration and the benefits are generic to any post-combustion CO2 capture system, I think, and you could see cost reduction to any of the technologies.
If I may quickly interact, just to comment on what you said, I think one of the also things that should be probably considered in this sort of integration from hydrogen and electricity is also the size that we are looking for. Because if we look at large size, large scale power plant, we have obviously a limited set of options. But perhaps when we consider an opportunity to have other sites process, that's when other technology might become more competitive and possibly overall as a cluster opportunity, you might see an overall advantage. So that's something that perhaps is interesting as a research question to look at in the future.
I think I agree, and I think until very recently, you're looking at projects in isolation, and now by the nature of having clusters, you're opening the door for potentially further opportunities for cost reduction integration. So, I agree. Thank you.
Thank you. Thank you, Vincenzo. Thank you, Matthew. One question from my side is about the steam required for the reboiler. I wonder where that steam is coming from. Is it? I didn't see that.
Oh yeah, sorry. So I didn't want to put too many complex slides, but basically so it's a generic CO2 capture process. You are extracting steam from the combined cycle of the CCGT, and you are extracting enough steam to capture the CO2 from the CCGT and the SMR.
All right, so it's a combination of both, the steam export from SMR and also from the power plant.
That's right. And also, we've looked at a case where you're increasing your steam extraction level to capture 99.8% of the CO2, and that's doable with that system.
Is there any option that you do not need to extract anything from the power side and everything can be supplied by the SMR plant?
No. So what we found is that no, if you want to there's a large amount of CO2 that's being made from the CCGT, so and that's where most of the steam is. There's more steam available in the combined cycle than there would be in the steam cycle of the SMR. So the SMR itself doesn't have enough heat available for heat capture.
Got that. Thank you. And also in your slide 16, you had the combination of gas turbine and SMR, and the exhaust of SMR goes to the HRSG. Just a thought, if you also transfer a portion of the flue gas out of the GT combined with the flue gas coming out of SMR to the HRSG, is there any optimization that can be done there?
So let me just, I'll share my slide again. So I just
sure. Yeah, here you have the flue gas right after a steam gas turbine goes to the SMR system, right?
Yeah.
If we have extraction of that, bypasses SMR and then goes to HRSG in order to have a higher heat load in the HRSG and producing more steam turbine and consequently more power, would that make any optimization of the plant?
No, I think what, so you're talking about bypassing the SMR?
Yeah, partially.
Partially. So what we've done, we scale our system so that the SMR is sized to use all the oxygen available in the flue gas of the gas turbine. Now, if you, I guess if you want to reduce the amount of hydrogen produced compared to power, in that case, yeah, you might bypass your SMR, or partially bypass your SMR, but then you still have to provide heat to the like the second SMR that you're bypassing, and you'd have I guess air combustion, so you would get some of the benefits of the configuration, but not all of them.
Okay.
So
okay.
When I show the ratio, it was 1 gigawatt of power to 2.3 gigawatt of hydrogen. obviously you can adapt that power ratio, but then the integration becomes less optimal.
Very good. Thank you very much. I think we have one, I'm conscious of time. We have 8 minutes left, but we have also one question from Cameron. Cameron, do you want to unmute yourself and ask your question, please?
Hi, thank you, Dr. Lucquiaud. This is a really interesting presentation. Going back to that slide 16, usual ratio of CO2 to hydrogen produced by SMR is something like 7:1 and 9:1, something in that range. Does this coupled production method with the CGDT and the SMR, does that change the ratio of your outputs of hydrogen to CO2?
No. So we've designed our system to the SMR operates conventionally. You know, the heat transfer in the furnace changes, but to the if you're on the side of the tube, you know, everything is the same, the temperature are the same, so there's no changes to the SMR function. So your hydrogen to carbon ratio.
Okay, great, thanks.
Right. Thank you very much. If there is no more questions, then thank you very much, Mathieu, for your presentation, great presentation, and also for the research that you and your team are doing. This is a great line of research. The blue hydrogen topic is an interesting topic, not only for the UK and the hydrogen economy that we want to develop in this country, but of course, globally, this is a hot topic. Suggestion would be, it would be helpful in order to really have a good understanding of your research to have a blue hydrogen price or cost sense checking in order to see where we are, and that would be the next presentation that you could present, you know,
that's
in
right.
following months for that.
Yes, so that's what we're working on now, trying to convert that into a levelized cost of hydrogen or a levelized cost.
Absolutely, I will be very much looking forward to that presentation too. Thank you, and with that I will hand it over back to Caris for the closing of the meeting. Thanks a lot.
So yeah, thank you very much, Mathieu. Really interesting presentation there. It was really interesting to hear more about the research that you've been doing over the last year or two as well. And thank you as well, Fatima, for excellent sharing as well today. Just to let everyone know what we've got coming up next week. So it's our last session of the summer web series, and we'll be hearing from Dr. Sarah Mander from the University of Manchester, and she'll be speaking to us on energy transitions in the industrial clusters, shielding, nurturing and empowering CCS. So I hope to see many of you next week for our final session. But thank you once again for your talk today, Mathieu, and thank you, Fatima, as well. And thank you everyone for your questions today. Have a nice rest of the day and the rest of the week.
Thank you, everyone. It was a pleasure. Thanks. Bye-bye.